Hello students, today I will start the gradient. The gradient, it is an operator and it is denoted by nabla, a special letter, and which is operated on a scalar field. It may be operated on a vector field or a vector function as a dot or cross product. But when it operates on a scalar field, then it is just operates it. There is no dot or no cross, because scalar field, it doesn't have any direction. It is not a vector. Now let's start with the definition of gradient. So simply grad, it is denoted by nabla, this symbol, and is defined by I del del x plus j del del y plus k del del z, where I, j and k are the unit vectors. And simply it shows that it is a differential operator, and this differential operator, it operates on a scalar field, and we suppose that phi xyz, it is a scalar field, just suppose. And after operating on this field, that is, if this nabla, this operator, gradient operator, operates on this field, scalar field, it becomes a vector quantity. Now simply I del del x, because I, j, k, the vector quantities, these unit vectors, are involved in this operator. So if it simply operates on a scalar field, it becomes a vector. So nabla operator, or the gradient operator, if it operates on a scalar field, it becomes a vector field. Now what is the geometrical representation, or how can we represent this gradient operator uh, geometrically? So look at this. So I already discussed in the previous lecture what is a scalar field. So look at this field, the orange shaded region. This is a scalar field, or a level surface, what we say. The specifically we can say it as a level surface. So this level surface, it is a scalar field, and it doesn't have any direction. That is, each and every point of this surface, it doesn't have any direction. Maybe it represent the temperature at each and every corner of this room. Suppose at this corner it has some temperature, at this corner has some different temperature, in the lower corner of this room it has some different temperature, but temperature is not moving. So we say it is simply a scalar field. Now after, look at this, fxy minus equal to minus cos square plus cos square x plus cos square y whole square. So this is the scalar field. Now if we operate the grad operator, on this fxy function, now it becomes a vector field. Now this vector field is represented by the lower portion. Look at this, the bottom plane, this becomes a vector field. So now these each and every point has some direction, and it is outward direction. That is, from the center all the directions are outward. So it has some direction after operating on a delta operator or a grad operator on this field, on this scalar field. So this is the geometrical representation of a grad function, a grad operator. Now we will start with the example. So 3x square y minus y cube z square, it is a scalar field is given. Now we need to find out what is the gradient of this field. So simply if there is no I or j component, I, j, k component, and simply a simple function is given without any I, j, k component, it actually generally shows us the scalar field or the level surface. Now this scalar field we now need to operate. To find out the gradient, we need to operate the grad operator on this function. Now let us suppose phi equal to phi xyz equal to this. So just suppose, now grad operator is operated on this function. So I del del x plus j del del y plus k del del z operates on this. Now simply we just, it likes a multiplication. It is not a multiplication, it is a operator, operates on it. So now del del x is operated on this function. So we write right del del x of this, now plus j del del y of this, and plus k into del del z of this. So simply now we are operating now this function, we got this function, and simply now take the derivative with respect to x. Delta x of this, it means y and z are constant here because this is a partial derivative, so only x is treated as a variable. And similarly, del y, x and z are treated as constants, so only y is variable here. Similarly, in case of z, del z, then x and y are treated as constant. So after operating del x, del y, and all these stuffs, we are getting this function. Now look at this function. I, j, and k is multiplied with these functions. So simply just to recall the previous lectures, this is nothing but a vector field. So this is the required gradient of this scalar field. Now look at the point. Now this scalar field, we need to find out the gradient of this scalar field at this point 1, -2, -1, and we have this function. After operating on this grad operator, we have this function. Now simply put the values of x, values of y, and values of z into this function, and after putting these values, that is x equal to 1, y equal to -2, and z equal to -1, we have this one, this function. So minus 12i, minus 9j, and minus 16k. Now look at this, which becomes a vector point. So after putting a particular point, that vector function, vector field function, becomes a vector point. Now come to example 2. So this is simply find the grad phi. It is, we are required to find out the grad phi when phi equal to ln r, ln mod r, where r is a vector. Now how can we solve it? Now since there is no specific point of r is given, so we will simply, in general, any vector can be considered as this xi plus yj plus zk. And since it is mod r, now we need to find out ln mod r. So mod of r, it means root over of x square plus y square plus z square, because this is the point. So if I take the mod of this vector, so obviously it is root over of x square plus y square plus z square. Now grad phi, now we know simply now take ln of this. Look at this, ln of r equal to this, half is a power, it is half into, it becomes half into ln this. Now simply take the gradient both sides. Now half is a constant function, it becomes outside, it is outside, and grad of ln this. And now just similar to the previous example, we will operate the grad operator on this function, and we will get this one, because del x of this, del y of this. Similarly, it's a partial derivative, so a y and z becomes a constant here. Similarly, x and z constant, and we are getting this function. Just take the 2 common, and 2 will be nullified, we are getting this function. So similarly, look at this, the numerator is xi plus yj plus zk, which is nothing but r vector, and the lower portion is the denominator is x square plus y square plus z square, it is nothing but the r square. So just look at this, mod r equal to this one, so if I square it, so it becomes x square plus y square, so z square. So just put here, so this is the value of the function. Now come to example 3. Here we see, find a unit normal to the surface this at 2, -2, and 3. So before starting the example, we need to remember that the gradient of a vector at any point, that is, suppose this is the level surface, this is a scalar field, this one, this level surface at any point x, y, z, if I find the gradient at this point, then this is actually, it becomes a normal to the surface. That is, a direction of the gradient is normal, that is normal to the surface. So simply it may be normal to this side, may be normal to the lower portion also. So I didn't draw the lower portion, but gradient means normal to the surface. So if I say normal, it may be in the upward direction, maybe in the downward direction. In both directions the normal works. So now find a unit normal to the surface this. So whenever we are required to find out the normal to any level surface, we just need to take the gradient of this scalar field. So our first duty is to take the gradient of this scalar field. Now grad phi, just phi function is given. Look at this, x square y plus 2xz equal to 4. So I am just taking this 4 this side, that is left side, and it will be minus 4 equal to 0. So just simply this we are writing minus 4. So phi, we consider phi equal to x square y plus 2xz minus 4. Now take the derivative take the gradient of this scalar field. Simply we are finding this function, we are having this function, and which is a vector field function. Now this function, this vector field function, what is the direction of this function? It is actually the normal to this surface. So we already have what is the direction of normal direction to this surface. This is the normal direction to the surface. Now we are required to find out the unit normal vector at the point this. So now we now put the point, this point, because a point is given. So after getting this gradient, we now have to require to find out what is the point. So just put the value of x, y and z, that is putting the point in this function, we are getting this. So these are vector points, so these are vector direction. So this direction is actually normal direction to the surface at point 2, minus 2 and 3. Okay, so just if I say look at this one, so this is the level surface, so this is the point 2, minus 2 and 3, and this direction is this one, this one. So if I say what is the normal unit normal vector, so this is a normal direction and we are having just a point. So how can we find out the unit normal vector? This is the formula of, we know the formula of unit normal vector is nothing but this vector divided by square root of 2 square, 4 square and this 4 square. So we just this is the unit normal vector to the normal to the surface. So this is a unit vector. So unit vector can be obtained by the vector, that is by using this formula, the vector and divided by square root of these three components, 2 the minus 2 square, that is 2 square, 4 square and 4 square, the square root of this. This is the formula of finding the unit vector. So this is the unit vector normal to the surface, this one. So now look at this, we write this one, this vector is this one, minus 1/3, and this, suppose at this point. So similarly we already know what is the this is the normal vector direction. So we already know normal vector can be upward and can be downward also. So this is the upward direction. So what will be the downward direction? So simply we just multiply with minus sign. So multiply with minus sign to this point, we are getting this one. So this direction, this is also a unit normal vector to this one, and the opposite direction, this is also another unit normal vector to this direction. Thank you. And in the next lecture I will discuss divergence and curl. Thanks for watching the video.